Welcome to Yaka Digital Network. The periodic table functions as a precise map of elemental behavior, where an element's position identifies its physical properties and chemical reactions. Early classifications struggled to map these patterns perfectly. Dmitry Mendeleev arranged elements largely by relative atomic mass, a system that resulted in several inconsistencies in the recurring chemical properties. Henry Moseley's X-ray studies eventually established a more reliable foundation. Moseley demonstrated that atomic number, the exact count of protons in the nucleus, drives an element's identity and periodic placement. The modern IUPAC table reflects this discovery. It is structured into 18 vertical groups representing valence electron counts and 7 horizontal periods corresponding to the highest occupied principal energy level. The grid is further organized into the S, P, D, and F blocks. An element's precise coordinates on this grid dictates its chemical identity, governed by 3 subatomic rules. The architecture of an atom is defined by a central conflict, the electrostatic pull of the positive nucleus against the distance and repulsion of the negative electrons. The first variable is nuclear charge. As the number of protons grows, the nucleus increases its electrostatic pull on the outer electrons, drawing them in tighter. The second variable is electron shielding. The inner shell electrons act as a repulsive barrier, shielding the valence shell from the full force of the nucleus and weakening that inward pull. The third variable is distance. When an atom adds a new principal energy level, the valence electrons move to a wider orbit. This added distance geometrically weakens the nuclear grip. By analyzing this subatomic tug-of-war, we can deduce fundamental trends that shape period 3 and group 2, from atomic size to their reactivity. Across period 3, from sodium to argon, atomic radius decreases. This happens because the nuclear charge increases with each added proton, while the inner shell electron shielding remains constant, allowing the nucleus to pull the valence shell closer. This structural shift directly impacts first ionization energy, the energy required to remove 1 mole of electrons from gaseous atoms to form 1+ ions. This chart plots the first ionization energy for period 3. We see a clear upward trajectory as the shrinking radius and rising nuclear charge hold electrons more tightly. However, there are distinct drops at aluminum and sulfur. Aluminum represents the first drop. While magnesium's outermost electrons are in the 3s subshell, aluminum places its final electron into the 3p subshell. This higher energy level is further from the nucleus, making the 3p electron easier to remove than a 3s electron. The second drop occurs at sulfur. Phosphorus has a stable arrangement of 3 unpaired electrons in its 3p orbitals. Sulfur adds a 4th electron, forcing 2 electrons to share a single 3p orbital. The resulting electron-electron repulsion makes it easier to dislodge one of them. These dips prove that subshell architecture and electron repulsion dictate the energy requirements of individual atoms. This bar chart shows the melting points across period 3. Here, the pattern depends almost entirely on the structure and the chemical forces broken during melting. The moderate rise for sodium, magnesium, and aluminum reflects their metallic lattices. The massive peak at silicon occurs because it forms a giant covalent network. Melting it requires breaking millions of strong silicon-silicon bonds. After silicon, melting points crash as phosphorus, sulfur, and chlorine form simple molecules held together only by weak London dispersion forces. This transition from ionic to covalent bonding also dictates chemical behavior. When period 3 elements react with oxygen, they create a distinct spectrum where ionic oxides like sodium oxide are strongly basic, while covalent oxides like sulfur trioxide are highly acidic. Sitting in the middle is aluminum oxide. It is amphoteric, possessing the chemical capacity to react with both acids and bases. The same bonding shift applies to period 3 chlorides. While an ionic chloride like sodium chloride simply dissolves in water, but adding a covalent chloride like silicon tetrachloride triggers a violent hydrolysis reaction, releasing acidic hydrogen chloride fumes. The shift from ionic to covalent bonding determines if a compound acts as a basic building block, an amphoteric bridge, or a volatile acid. Moving downward to group 2, reactivity steadily increases from beryllium to barium. The addition of electron shells increases both the distance from the nucleus and the shielding effect, making the 2 valence s electrons easier to lose. To understand the behavior of the ions these metals form, we measure their charge density. This is the ratio of an ion's charge to its physical volume, dictating the concentrated electrostatic pull it exerts on neighboring molecules. Because of charge density, elements can share properties diagonally across the table. Lithium and magnesium sit in different groups, but their ions have nearly identical charge densities. As a result, they mimic each other chemically. Both form nitrides directly with nitrogen and produce sparingly soluble carbonates. We apply charge density to the thermal stability of group 2 carbonates. A small magnesium ion has a high charge density that distorts the neighboring carbonate anion's electron cloud, weakening its internal carbon-oxygen bonds. Thus, magnesium carbonate decomposes easily under heat. Barium sits lower in the group. The barium ion is much larger, resulting in a lower charge density. It polarizes the carbonate anion much less, leaving the internal bonds intact and requiring significantly more heat to break the compound down. An ion's physical size determines the dimensions of its crystal lattice, while simultaneously engineering the thermal breaking point of the compound. These specific Group 2 properties form the backbone of heavy industry and agriculture in Uganda. The precise thermal decomposition of limestone, calcium carbonate, into calcium oxide and carbon dioxide is the fundamental chemical step required to manufacture cement. In agriculture, the basic nature of Group 2 hydroxides is applied to soil management. Farmers use milk of lime, a suspension of calcium hydroxide, to neutralize acidic soils and improve crop yields. This graphic shows the contrasting solubility trends of Group 2. Moving down the column, the solubility of Group 2 hydroxides increases. However, the solubility of Group 2 sulfates reverses, decreasing sharply as you move down the group. Barium sulfate is so insoluble that chemists leverage it in the laboratory. The immediate formation of this heavy white precipitate serves as the definitive qualitative test for the presence of sulfate ions in a solution. Industrial chemists use these predictable periodic gradients of solubility and thermal stability to manipulate raw earth into modern infrastructure. Now it is time to move from the concepts to applying first principles to quantitative data. This data table illustrates successive ionization energies for a single element. A sudden, massive jump in the energy required to remove an electron, like the one seen here between the third and fourth removal, identifies the atom's inner shell boundary. It tells you immediately that this is a Group 13 element. Utilize your competency-based reading notes to practice deducing the identities of unknown elements purely from these datasets. You can watch more videos for all classes here and get all content at www.yaka.com.